Okay, I think we're going to get started here. Thanks everyone for joining us here. I know it's the end of the day and probably pretty exhausted from 2 days of KubeCon. But we're going to be talking to you today about Fluent Bit, which is a logging agent that you might be familiar with. And we're going to talk about how you can use Go to integrate with Fluent Bit and extend your logging capabilities using Go. So that's the main topic. Just a quick show of hands. How many people here have or are regular users of Go? Okay, so a good amount of you. So this will be useful for you all. So my name is Jason Keene, and my colleague here is Warren Fernandes. We work for Pivotal, and we work mainly on observability tooling for Kubernetes. And we're both really avid Go users. We love using Go. And Pivotal is, as a company, has embraced Go pretty heavily. So pretty much any problem we encounter, we see if it's possible to solve using Go. And Go is a language that is increasingly important in the cloud infrastructure space. Kubernetes, as I'm sure everyone's aware, is implemented in Go. Pretty much all the tooling that we use is somehow related to Go or implemented directly in Go. So it's incredibly important for us as a company and as a community. So today we're going to be talking about kind of our story with Fluent Bit and Go and why we decided to choose Fluent Bit. So folks might be familiar with Fluent D, which is a little bit better known than Fluent Bit. Fluent Bit's kind of like a newer project. So we're going to dive into like why we chose Fluent Bit over Fluent D. We're then going to kind of go over the architecture of Fluent Bit, kind of do a little dive into how Fluent Bit works internally, and then we'll cover the Go interface, so how Fluent Bit interacts with Go. And finally, we're going to cover some of our ideas and plans for moving the ball forward in regards to using Go with Fluent Bit. So let's start with why we chose Fluent Bit. So the product that we were working on is observability capability for Kubernetes, and one of the aspects of that is collecting logs. And a lot of our customers use syslog as a protocol, so we basically needed to get all the logs off these clusters and ship them to syslog destinations. Message reliability was a primary consideration for us, so we wanted to have a system that would not just forget about messages. We wanted something that if a log message was written out by the workload, we wanted to eventually get delivered to the logging destination. So that was our primary consideration. We wanted to have really good support in the community, the Kubernetes community, and preferably a project that's part of the CNCF. Go, again, is like a first-class thing that we want a project that has first-class support for Go. RFC 5424, so the syslog specification is standardized in the IETF RFC 5424. A lot of syslog implementations don't necessarily follow this standard, so we wanted to make sure that we had a standards-compliant implementation. And finally, in looking for a agent, we were looking for something that wouldn't consume a lot of resources and would be somewhat performant. So those are all our criteria in order. So let's take a look at Fluent D and Fluent Bit and kind of how they differ in these criteria. So just kind of overview of both of these and how they differ. So Fluent D is implemented in Ruby and has some gems that use like C modules for performance critical code. So stuff like the message pack capability is implemented in like a C extension for Ruby. But most of it's implemented in Ruby. Fluent Bit itself is implemented in C. Fluent D, as you might have heard, has a really vast ecosystem of plugins. Last number I heard was over 1,000 different plugins available for Fluent D, which is incredible. Fluent Bit, on the other hand, is a relatively new project, so it has less plugins, less capability in that regard. And the plugins for Fluent Bit are mostly statically built with Fluent Bit, so they're not things that you kind of can just like pull off the internet and start running. So there's less of those. So there's only around 54 last time I checked. Fluent D you can extend with Ruby really easily. Just write a class, and there's different extension points. Whereas with Fluent Bit, you kind of, if you want like a first-class support for a plugin, you want to implement it in C. There are options for Go, and that's what we're going to be going into today. And then there's also some Lua capability as well. Fluent D, when it comes to memory and CPU, just in idle state, Fluent D will consume about 40 megs of RAM, and Fluent Bit will consume much less, around 500 kilobytes. And as well as memory, CPU, Fluent D consumes a little bit more CPU than Fluent Bit, just in idle state. Fluent D is kind of targeted for aggregation type role. So since it has this broad support for input, output plugins and filters for manipulating data, it's really suited for that role where you're kind of ingesting a lot of data and sending it to the appropriate location. Whereas Fluent Bit has some of those capabilities, but doesn't have the large amount of plugins, so it's not really well suited for that role. But it is better suited for kind of like the edge collection of data. So it has really good input plugins, and it's really performant and doesn't consume a lot of resources. So it's better as like a daemon set, so an agent that you're running your cluster on every single node. And finally, both Fluent D and Fluent Bit have support for something called the forward protocol, which just allows them to interoperate. So it's not really a question of Fluent D versus Fluent Bit. It's really which technology is appropriate in the right location. So if you want to use Fluent D where it makes sense, you can do that, and you can interop with Fluent Bit using this forward protocol. So going back to our initial criteria, message reliability. So both Fluent D and Fluent Bit do a really good job at message reliability. They both support buffering in memory into disk. That's something that was introduced recently in Fluent Bit a few months ago. They support buffering, and they support retrying of messages. So if a message fails to send, you can have the engine retry the message for you. Kubernetes support, both of them have really good first-class support for reading log files off a disk, and then a Kubernetes metadata filter for taking the log message, figuring out what pod and container it's associated with, and annotating the message with that information. CNCF status. So Fluent D is a recent graduate of the CNCF. So I think it's the 6th project that was graduated from CNCF. So it's really mature. Fluent Bit, on the other hand, is kind of a newer project. It's technically a sub-project of Fluent D, so it's still kind of part of that CNCF status, but it's still relatively new. Go support, Fluent D doesn't really have any support for Go. Fluent Bit supported at the time of us going through this criteria, only supported output plugins. RFC 5424, so there was an implementation of a syslog gem for Fluent D. When we investigated it, it turned out to not really be 5424 compliant, and if you use it with a Kubernetes cluster, since the tag is the file path of the log, and that actually gets written out in the syslog message as the tag, it actually caused the Ruby interpreter to throw an exception. So pretty much if you use it with Kubernetes, it doesn't really work too well. So that wasn't really a good option for us. And then Fluent Bit didn't really have support for syslog output plugins at the time, and I think it has input plugins support, but it doesn't have support for sending out messages via syslog. Resource usage, so like I mentioned before, both with resource usage and performance, Fluent Bit kind of wins out in that regard. So given kind of all these criteria, we decided Fluent Bit would probably be the best choice for us. And the main thing that came down to is ease of implementing the plugin using Go. So yeah, that's it. I was going to talk about the architecture of Fluent Bit.
All right, so I'm just going to cover a high-level overview of the architecture of Fluent Bit. Just FYI, most of the stuff that I'm talking about has already been covered by Eduardo Silva, who's one of the core maintainers of Fluent Bit. And this is a screenshot of his talk last year in KubeCon Seattle. How many of you guys went to the talk a couple hours ago? Yeah, okay, cool, we have one. All right, new stuff for you guys. Yeah, he gave a deep dive of the newer stream processing support for Fluent Bit, but I won't be covering that. All right, so this is essentially the logging pipeline of Fluent Bit. You might have seen this on day one keynote stage, very similar diagram. I'm going to try and cover this pretty quickly. So one of the things that you have to understand with Fluent Bit, it was designed to be a data analysis tool. And essentially it was designed to be ubiquitous across a lot of platforms, right? It was actually designed for an embedded world. And not really with any sort of structure in mind. It was trying to be as flexible and, ubiquitous across all platforms. So they tried to build the pipeline with a lot of flexibility. So let's start with stage one. So the first thing that Fluent Bit does is it has an input stage. This is where it actually collects the logs, right? And this could be from tailing files to reading off the network or various myriad of ways. One of the key things that the input stage does is it actually tags. The tag is specified in the configuration for that instance, and it says, okay, I'm going to tag these records with a specific thing, like, I don't know, host name or cluster name, whatever. From there on, the chunk of data gets sent over to a parser. Now, you have to understand that this was built again for data analysis. I'll keep reiterating that. And we can't expect our data to always be structured, right? Like in our Kubernetes world, it's great because they're essentially in JSON format. But the intention for this tool was not to assume that your logs are structured in JSON or log format or whatever. So you can literally get a string of text that are the tokens are 2 spaces away. So this parsing stage does the important job of normalizing that data and adding structure to those log messages, right? From then on, it goes to the filtering stage. Now, this is actually, in my opinion, like one of the most important things in Fluent Bit. So this filtering stage allows you to, one thing it does, it allows you to enrich your data. What does that mean? So in our world, in the Kubernetes world, right, the log that comes in from the Docker file, the Docker log file is you have a JSON with a key of log, stream, which is standard out or standard error, and then I think a timestamp. And that's very basic, but if you use the Kubernetes metadata filter, it enriches your log with all this metadata of where did this log come from, the pod name, the container ID, labels, annotations. Again, built for data analysis, so you have now all this rich metadata that you can use later downstream. So that's one important job that the filtering stage does. The next important job is removal of data. If some of you have used tools like Splunk, you can understand how expensive a log can be in storing every single log. And sometimes you want to do that, sometimes you don't need that. So this is the stage where you can say, oh, if it doesn't match the tag or it doesn't have this word, like the word error in it, I don't care about it. Get rid of it. Remove that data. And so it kind of lightens that load. After that, it goes to the buffer. Jason mentioned before that one of our criteria was reliability. And we've been in the observability space working in Cloud Foundry. One of the things we kept on seeing was a back pressure when the outputs fail to send messages fast enough. So having this buffer, by default, it's like an in-memory buffer. But I think as of version 1.0, you can configure Fluent Bit to have on-disk, like a storage mechanism for the buffer. And this buffer then allows Fluent Bit to do message retries. Then comes the routing stage, which literally, remember the tagging on the input right in the beginning. It does a wildcard or regex match on the tag and says, okay, things that are tagged with cluster A sent to output A, cluster B sent to output B. So, yeah, and then you have outputs. And the stuff that we're talking about is the output side of things. And Jason mentioned like 54 plugins right now, or 50-ish plugins in Fluent Bit. These are the stages that can be pluggable, right? And again, they did this so that you are empowered to be as flexible as you need. So if things don't work out, hey, write a plugin, right? And just in our case, we just didn't want to write a C plugin and have that statically linked. So we saw that Fluent Bit gave us the ability to dynamically link Go plugins, which is why we're here. All right, so let's go on to a little bit of the internals. So Fluent Bit runs as a single thread. Remember, I said the initial intent was to run it in an embedded system, so it had to be very lightweight, right? And everything in Fluent Bit is configured with this config file, everything. So things like flush intervals, the service level config, to the inputs and outputs and all of the instances that you need to configure. And the first thing it does when it reads in and loads this config file is looks and sees, oh, are there any Go plugins? Oh, there are. You have configured perfect. I'm going to load those shared objects in, and I'm going to load these plugins in and register the plugins. And the first thing it does is says, okay, now this Go plugin is in my list of output plugins, right? And then it goes on down the config file and it says, okay, let's initialize each of these input plugins, filters, and output plugins. So as part of this initialization process, what happens is, so think of it's saying, okay, I'm going to go through my list of input plugins, and there's an input plugin that says, okay, I need to read data from some network server, so I need to set up a TCP connection. So as part of that initialization, this input plugin says, okay, I'm going to set up this TCP socket, and I'm going to start reading data. And then what happens? Remember, Fluent Bit is running as a single thread, right? And I kind of mentioned the words scheduler and event loop there, so it kind of gives you a hint. So everything just stops, right? And Fluent Bit's like, hey, I got other stuff to do. I got other plugins to initialize. What's the process? So what Fluent Bit does is actually it invokes this age-old flow control of coroutines, right? And this coroutines essentially allows for a cooperative passing of execution between the plugin and the engine itself. So what the input plugin does, it says, okay, I'm going to set up the socket, and then, hey, Fluent Bit engine, here you go. Let me know when you see data coming through it, when data flows. Fluent Bit engine says, I'll take care of it, and goes on and starts initializing the rest of the plugins. And suddenly, hey, I got some input. I got some data that's coming to this socket. The socket's ready to be read. So it then resumes control back to the input plugin and says, you are ready to read. And it then input plugin says, thank you, and says, okay, I'm going to start reading records. So there's this really nice cooperative flow between the engine and the plugins. Now, as the input plugin reads the data, it's just reading like the bytes in, but internally it's represented as a binary serialized message. It uses message pack for its binary serialization and creates these records. And you can think of a record as a timestamp and like a key value pairs of the message map, right? And it starts stacking up these records, and it creates this chunk of records. And then at a certain point, it says, okay, I got this chunk. I'm going to tag this data, send it on to the next stage. The filtering does the matching on this tag. It goes to the list of filters. It says, okay, this record, I'm going to append some data and enrich it. And the other records is like, I don't care about you. I'm going to get rid of you. From there on, it goes to the buffer, and it gets stored in the buffer. While this is all happening, the event loop kicks in, and they have this flush interval, which is configured. The flush event comes in and says, well, all right, time to send the data on through. We got to send the data out. So Fluent Bit internally, what it does is it creates these tasks for each of the input instances and says, okay, I'm going to create these tasks in my event loop, and we'll start flushing data out. And again, that same dance happens, right, for the output plugins, because the output plugins most of the time is network I/O out. So it says, okay, it's time to send the data out. So again, we have this cooperative dance between the engine and the plugins. And once the output, the last thing that the output plugin does is when it sends the data out, it can actually respond back to the Fluent Bit engine saying, hey, everything went well, or something went wrong, can you retry sending that payload? And Fluent Bit will say, okay, I got that, I'm going to retry sending that same payload through, or error out and say, you know what, don't bother resending that data. So that's kind of how the gist of how the flow of reading in data, sending it all the way out, and our Go plugin kind of fits in that same sort of space, the Go and the C plugins for the output side of things. All right, Jason's going to cover the Go interface side of things.
Thanks. All right, so this is the fun part for me. So how does Fluent Bit interface with the Go? So Fluent Bit is implemented in C, and we have some code written in Go that we want to interact with Fluent Bit. You may be aware of something known as CGo, which is like the interop capability between Go and C. So we're going to be using that. But how exactly do we want to kind of call from C into Go? So that's going to be handled by just regular dynamic linking. So the C program is going to call DL open DLSim in order to call into the shared object that we provide. But you might be wondering, like, how does this .so get created? Normally when I compile things with Go, I get a static binary. That's one of the major selling points of Go is static binaries. So how do we generate this .so? So there's this flag that you can give the Go compiler when you say go build. You can say build mode, and there's various options that you can give that flag. And the ones that you're probably familiar with, or at least most people would be familiar with, are archive and exe. So archive and exe. Archive will generate those .a files that you have in your Go path under Go path pkg, and then exe is just kind of like your normal build mode for building a static executable. So an archive will get built when you're building a package, and an exe will get built when you're building a main package. So those are like the regular modes. Some of the more esoteric ones are plugin. So you might be thinking, plugin, that sounds like what we want to use. So plugin actually is used to generate a dynamically linkable shared object of Go code that is intended to be called from another Go process. So it's not exactly what we're looking for. We're looking to call into the Go code from C. So one thing that we could choose here is a C archive. What that'll do is it'll allow us to call from C into the Go code, but it'll generate as a static archive. So it's not exactly what we want. So the one, as you can tell here, that we want is C shared. So that'll allow the C program to dynamically link against a shared object that we compile. So what does that look like? So if you're in Go and you want to create one of these shared objects, you just create a main package. You say, I want to import C, which is like a pseudo package to signify to the compiler you want to use CGo. And then you just kind of write your functions as you would normally. And you just put this little comment above the function that just says, I want to export this into C. So this is like the extern capability. So it just makes it a global symbol in your symbol table. And then you have to have a main dot at the bottom, just kind of as boilerplate. The compiler requires that. So you just have to include that. But that's about it. So you just say go build, output plugin.so, and then build mode C shared. And that will generate a plugin.so. And if you use something like readelf to just dump out the symbol table, you can see there's the dynamic symbol table has a symbol for my awesome function, which is what we want. We want to have a symbol that we can link against from our C program. So that's what we wanted. So that takes care of generating this plugin.so. But you might also be wondering, well, C and Go are entirely different beasts. Like they have different memory layout for different types. They have different calling conventions. So like, how do we manage the differences between these two different languages? So the first thing is calling conventions. So C's calling convention is entirely different from Go. Go has its own special calling convention. So how do we minimize that difference? So the compiler actually just takes care of that for you. When you compile that .so file, in addition to the myAwesome function symbol, the original Go function is generated as well, just not as an extern symbol, and it's just main.myAwesome function. So that's like your Go function, and then the function that it's exposing to C is a function that follows the C calling convention and then knows how to follow the Go calling convention and just calls into your Go code and handles kind of the mapping between those two worlds for you. So you don't really have to worry about that. What about memory layout for different types? So in C, like a char star is different from a Go string. So how do we manage these differences? So on the left-hand side here, you can see all the types that you would normally have in C. And on the right-hand side is how you represent those types in Go. So if you want to refer to those types from Go code, void star is unsafe pointer, char star is a pointer to c.char, so on and so forth. Some of the interesting ones are like structs, enums, and unions. You just say C struct and then underscore followed by the name of the struct to kind of get a reference to that type in Go. And then the inverse, going back into C. So if you want to refer to Go types in C, when you compile your .so, it'll actually give you a header file as well. And that header file will contain definitions for all these types. And so you just kind of pound and include that header file in your C code, and then you get all these types defined for you. So things like strings are represented just as Go string, Go slice, Go int. So Go slice is just kind of like the slice header, so it doesn't actually have the type information for your slice of byte, so it'll know it's a slice, but not that it's a slice of byte. But yeah, most of these things are pretty straightforward. And then CGO provides capability for conversion between different types, so different memory layouts. So the important ones are like strings and bytes. You want to be able to convert from like a C string to a Go string and vice versa. And same thing for like bytes. You want to be able to convert from like a slice of byte, which is a slice header and an underlying array. You want to be able to convert that into a bit of memory that C can handle. So what about functions that have multiple return values? That's not really something that C supports. So say we had this function here that had multiple return values, and you exported it. What would the compiler generate for you? So in that header file that gets generated, it'll generate these kind of struct definitions. And these are just kind of a composite type of all the different return types. So you can access those from C. And that's just what gets returned from the function. So that entire struct, not a pointer to it, but the entire struct itself will be on the stack and get returned to you. So how do you write a Fluent Bit Go plugin itself? So I just kind of explained the generic interface between C and Go for what we want to do. So what are the specifics about like using Fluent Bit using this interface? So there's only 4 functions that you have to implement. And these 4 functions are register, init, flush CTX, and exit. And we'll go into kind of the details of these. So register, there's some helper functions and an output package that you can use. And basically the job of the register function is to allow the Go code to communicate back to the C code information about the plugin. So in this case, we're setting the plugin's name and a description for the plugin. The init, so the register gets called once per shared object. So you can kind of think of that as global for your plugin. The init, however, gets called once per instance. So if you configured like say 5 different instances of syslog output plugins, then this would get called 5 different times. And in this function, you typically read from the config. So there's just a FLB plugin config key. So you can just read whatever key you want out of the config. And then the important bit here is to set the context. So you call FLB plugin set context, and you can set any arbitrary like Go value as the context for that instance. And that's important later on when we're flushing to be able to disambiguate invocations of the flush. So this is what the flush looks like. So the first thing we do is kind of reconstitute that context. And we just do that by making a call into this helper function called getContext. And then we have to type assert it because it loses its static type information. It still has its runtime type information, but we need to reconstitute it as like the original type. So in this case, it was a string. So we type assert it to be a string. And then there's other helper functions that allow us to then decode the data from Fluent Bit, all the messages that are encoded via message pack. We can decode those and handle them kind of one by one. In this case, we're just kind of logging out the data. And then at the end here, as Warren mentioned before, you can kind of return 1 of 3 values. Either everything was OK, or you need to retry, or there was an error. And then finally, just kind of like an exit, tear down, clean up function that you can implement. So you can put whatever you need to in there. So yeah, that's pretty much it for the Go interface for Fluent Bit. I'm going to hand it back off to Warren.
Cool. All right. So moving forward, so what we kind of explained to you was our use case where we needed to output stuff in RC5424 syslog format, right? And we working with the Fluent Bit teams like Eduardo, and we were able to add some, contribute some value in the sense that right now, Jason had mentioned about multiple instances. So you can have now multiple instances of your syslog plugin in the configuration file, and you can actually like sends to different destinations, for example, right? But what else can we do to better support this Go plugins, right? Let's say you guys love this talk, you tweet about it, and then you like leave this room and you say, I'm going to build some Go plugins for Fluent Bit. And I'm going to build multiple different Go plugins because that's what I need. I need to send syslog 5424 or my awesome protocol or whatever. So you have multiple different Go plugins, and you follow this process, and then you'll kind of realize that, hey, this thing that was supposed to be lightweight is no longer as lightweight as it seems, right? Because as you can see, each time you build this Go plugin as this C shared mode, you have the entire Go runtime kind of packaged with it, right? So we had an idea of like improving this in the future. Just to go back to the Go build modes, you have this plugin and the C archive. So let's take a look at that, how we can achieve that. So one of the ideas we had was having a Go plugin manager that's built with the C archive build mode. That way you can statically link it with Fluent Bit, and that contains the Go runtime. And then that plugin manager then loads Go plugins that are literally built with the plugin build mode, and that's as simple and clean. You don't have to worry too much about the C-Go side of things. That's just one idea we had for moving forward and improving plugin management. Another idea we had was establishing a versioned ABI or application binary interface. The context, for example, that you have to pass in requires a certain way the struct is defined. So if we update Fluent Bit to have anything more, then your plugin kind of goes off scope. So establishing a versioned ABI allows you, maybe the plugins during registration time can say, okay, I conform with ABI version 1.2, and Fluent Bit's like, all right, you're good to go. So that was another thing, establishing a versioned ABI so that nobody breaks in the future as Fluent Bit revs versions. The next thing is, again, this is only for output plugins. So we have input and filter plugins that can be also implemented in Go. In fact, there's a PR opened for supporting filter Go plugins. So thank you for that, whoever you are. Then another thing, metrics and logging. So so Fluent Bit actually exposes a metrics endpoint that allows you to get metrics of the records flowing through your system via JSON or a Prometheus form, right? And it tells you like all the records that goes in your input and that have been filtered out and then have been successfully sent. This works great for the C plugins that are statically linked in Fluent Bit. So one of the ideas we had is to support that for Go plugins as well. Right? And all of this right now is kind of work done in this Fluent Bit Go repo. Again, we are at a very early stage of us doing this Go support for Fluent Bit. So if you are interested in this space, we want you to join the Fluent Bit Slack channel on Fluent All, I think it's the Slack domain, and make issues and PRs and contribute to Fluent Bit Go. Eduardo has been very open and getting these PRs through and improving the ecosystem. So yeah, and that's about it. Thank you very much.
Are there any questions?
Thanks for the talk, very interesting. I have a question about what Go gives you, because I would kind of argue that what you showed, while it's very, very interesting, I wouldn't call it really Go code, because you still have to deal with these types and the conversion and so on. So I'm assuming that maybe you could talk a little bit about where Go actually helps you, where it makes it simpler to use Go instead of writing the plugin in C.
Right.
Yeah, so we tried to handle most of the complexity of like dealing with C types in the interface and these kind of like helper functions that we provide. So ideally, like as we advance, like the package will provide most functionality that a normal Go programmer would want, just using these helper functions. So you just call into those helper functions, and they kind of hide all that complexity behind them. As far as like what like it gives you, like, from our perspective, like we have really robust implementations of network protocols and like different libraries that we developed over the years in Go, and just being able to leverage that and the huge ecosystem of Go, third-party packages and the standard library, like it's just a wealth of treasure as far as like how much there is out there for you to take advantage of. Whereas in C, you kind of have to bring your own stuff, and I mean, if it's something that you're familiar with, if that's kind of like your domain, then you have that capability to use C as well. But having a lot of Go experience, we feel like
yeah, I think one of the requirements from product was also time to market. Since we were very familiar with Go, I mean, it's not like we were afraid of doing the C thing. It's just in order to get the stuff out, get it out, read, iterate. We were able to move faster with Fluent Bit, with writing Go plugins, and we did that. And then we were like, oh, well, this is great. How can we improve on it? And that's kind of what kind of led to all of this.
Also, did you try hiring people who can write in C? Any more?
Thank you. It's more of a Go question, I guess. Do you know when the garbage collector will be called in Go when you run it this way? And also, did you measure any overhead in running Go code instead of C?
Yeah, you want to take that, Jason? That's a good one. That's a good question.
So when the garbage collector is invoked was your first part of your question. So like if you wanted to invoke that, you can obviously do that manually. It just kind of whenever the runtime decides to run. So whenever you call into Go code, if you ever look at the output of the compiler, it has kind of hooks into the runtime where it has an opportunity to run the garbage collector. So I'm not really familiar with the details of like when it might run, but it has the opportunity to run when you call into the Go code. And then what was the second part of your question?
Overhead.
Overhead. So the major overhead that we've ran into is when you have multiple types of Go plugins dynamically linked at the same time, you have a duplication of the Go runtime in every single plugin, which is far from optimal. So that's kind of like what we're working on now, is improving that to where you don't have any of that overhead. And in the experiments that we ran, which is having a single Go runtime and calling into the plugins directly, it's the same function call overhead that you would have normally in Go. So there's no additional overhead.
Any questions?
Hi, great talk. Did you consider file beats, which is also written in Go for your sending of files, which is it's an Elastic project.
Well, what was the technology name again? The tool name, I guess?
It's the Beats project from
Beats.
the Elastic, and there's a file Beats.
No, we at least I haven't come across the Beats project, but thank you for that. We can take a look into that. Anything else?
Anything else? Okay, so thank you again for a great talk.